Bueno, espero que se escuche. Hoy tenemos como invitado en el coloquio a Matías Pavés Signe, quien hace muy poquito se está incorporando a nuestro departamento como profesor asistente. Entonces quiero leer un poquito algunas cosas sobre Matías. Entonces Matías hizo toda su formación en la Universidad de Chile, acá se tituló como ingeniero civil matemático el 2016 y obtuvo su doctorado el 2021 también acá, bajo la dirección de Maya Stein y Jeff Hahn. Entonces, después de una primera etapa como postdoc en el CMM, continuó su carrera en el Reino Unido. Fue como Research Fellow en las universidades de Birmingham y de Warwick. Y más recientemente fue parte de la cátedra de excelencia CMM CNRS para jóvenes investigadores también del CMM. El año pasado también se adjudicó un fondo regular y recibió durante su formación la tesis doctoral de la. Su investigación se sitúa en la combinatoria extremal y probabilista con contribuciones en teoría de Ramsey, que es lo que vamos a escuchar hoy. También en incrustaciones de estructuras de grafo y estudio de condiciones para garantizar existencia de ciertos grafos en modelos pseudo-aleatorios. Entonces, más que seguir hablando de tu investigación, te doy las gracias por estar con nosotros y te dejo la palabra para que nos cuentes un poquito sobre Ramsey Numbers of Trees and Related Questions.
Gracias, José. Abelio me pidió que hablara en inglés porque hay gente que no habla español. Así que voy a cambiar. I'm gonna switch to English now. ¿Sí? ¿Qué?
No importa.
Yeah, yeah, yeah. Sí. So if you have to complain about something, you have to complain to Abelio. Okay. Anyway, thanks. So I'm gonna talk today about an area I've been researching in the last 3 or 4 years, which is Ramsey theory. So Ramsey theory is a very important area of mathematics right now. It appears across many different areas. I'm gonna try first to show you why it's so important. And the meta statement says essentially that total absence of structure is impossible. And a typical result in Ramsey theory says that in any finite partition of some Ramsey structure, whatever it is, there's a well-organized substructure which is completely contained in one of the parts. So we typically don't state Ramsey results in this way. We rather use colorings. So let me start with Ramsey theorem, which is from 1929. To state the result, let me give some definitions about graphs. So given a set X, the complete graph with vertex set X, it's denoted by Kx. It has vertex set X, and all possible vertices, pair of vertices, which are distinct, form an edge in this graph. The original Ramsey theorem, this is Frank Ramsey, says that given any number R, however we partition the complete graph, the edges of the complete graph on the natural numbers in R parts, there's always an infinite set X and an index I, such that for every X and Y in this set, the edge XY is in this set EI. So in general, we don't state Ramsey results in this way. The way we state them is with colorings. So the idea is the following. So we color the edges of the complete graph on the natural numbers with R colors, like this. There's always an infinite set X and a color I, such that the complete graph with vertex at X is monochromatic in color I. That's the original Ramsey result. So this result is a generalization of the pigeonhole principle. In which way? So let me briefly sketch the proof of this result using for two colors. The idea is the following: two colors, let's say red and blue. We color the edges of the complete graph on the natural numbers, and we pick the first number here, 1. So this vertex has red neighbors and blue neighbors. So at least one of the two colors is an infinite set. Let's say the blue neighborhood is going to be an infinite set. We define x1 to be all blue neighbors, and call this vertex, this first vertex is going to be a blue vertex. So here we have the first vertex, which is going to be x0 here. We pick x1 as the minimal element of x1, and we repeat the argument. So x1 has red neighbors, blue neighbors. One of the two colors must be infinite. And we pick x2 as the infinite monochromatic neighborhood of this vertex x1. And we color x1 accordingly. So we repeat this argument ad infinitum. So we have an infinite sequence x0, x1, x2, x3, and so on. So that x0 here has only blue neighbors to the right, x1 only has red neighbors, says, to the right, and so on. So the vertex xi has an infinite monochromatic neighborhood. In this case, it's red, and therefore it has only red neighbors to the right. So we have only two colors, and we have an infinite sequence. So at least one of the two colors must appear infinitely many times. So let's say in this case it's red. So what we found here is an infinite set, so that all the edges here are in red. So this is my monochromatic complete graph that I promised you. So this is just using the PG Hall principle many, many times. So this beautiful result of Ramsey is not the first result in Ramsey theory. So actually, there is an even earlier result by Hilbert. So this is the Hilbert cube lemma from 1892. It says that for any coloring, finite coloring of the natural numbers, we can find a monochromatic cube. What I mean by this, we can find some number, so base point A, and numbers lambda 1 up to lambda k, such that all these sums have the same color. Why is this a cube? Because if you this is going to be the base point, you can think of these things as coordinates. So this is a three-dimensional cube, but you can ask for any dimension k. Another result is by Schur from 1916. It says that, okay, for any number of colors R, if n is large enough, and if we color the natural numbers, sorry, the first natural numbers with R colors, we can find three elements, x, y, and z, such that they all have the same color, and they have this arithmetic relationship. So x plus y is equal to z. So this result is quite important because it was used by Schur to prove that Fermat's last theorem doesn't hold in the integer mod p. Another very nice result says that vector spaces are also Ramsey. This result is by Galay, Lev, and Rothschild from 1972. It essentially says that if we color the point of a vector space, a finite vector space, finite dimensional vector space, there is a subspace which is going to be monochromatic. But more generally, it says the following. We have some finite field F. We have R, the number of colors. We have integers L and K. So if we color the k-dimensional subspaces of F to the n, we can find a subspace of dimension L, such that all the k-dimensional subspaces have the same color. But here, if we put k equals 0, we can find a subspace of dimension L, such that all the points have the same color. So essentially, we are finding a monochromatic subspace in this. No matter how we color this F to the n, we can find a subspace of dimension L fixed, so that all the points have the same color. So let me mention two results of my taste that use Ramsey ideas, not Ramsey theorem, but Ramsey ideas as key steps in the proof. So the first result is a very famous result of Semeredi, which solved a very old conjecture of Erdos and Turan. So this is the famous Semeredi theorem from 1975. It says that if you have any set A of the natural numbers of positive density, then it contains a non-trivial arithmetic progression of length k, where k is any fixed number. So this result has many implications in many areas of mathematics, in particular in graph theory. Not the result, but the proof of this result has many implications in graph theory, number theory, ergodic theory, and Fourier analysis as well. Another very interesting result is a very old conjecture by Banach, which was solved by Timothy Gowers in 2007. So Gowers proved that every Banach space X has a subspace W with either contains an unconditional basis or it is hereditary idempossible, whatever it means. The thing is, this solves a very old problem of Banach. This is more readable. So this says that if we have a Banach space, an infinite Banach space, such that is isomorphic to all of its infinite dimensional subspaces, then X must be a Hilbert space, a separable Hilbert space, an L2. And again, Ramsey ideas are really present in this proof. So let me now go back to graphs and try to explain the first element of the talk. So in graph theory, which is possibly the area where Ramsey theory is more studied, has been more studied, the fundamental object is the Ramsey numbers. So for a graph G, the Ramsey number of G is, which we denote by RG, is the minimum number n that no matter how we color the edges of the complete graph on n vertices with two colors, typically we use red and blue, we can always find a monochromatic copy of my graph G. So this is very similar to Ramsey result, but Ramsey original theorem. But in Ramsey theorem, we have not a finite graph, but rather a countable graph, a graph on the natural numbers. So the first question is obviously why this number exists. So let me try to explain why this actually exists. So suppose for a moment G is the complete graph on T vertices. And let's try to run the same argument as before. So what we did before, we picked the first vertex. We look for an infinite monochromatic neighborhood. Here, obviously, we don't have an infinite number of vertices. But what we can say is that, OK, x1 has at least a half of the neighbors in one color. So let's say this is x1. We can find in blue, say, at least a half of the vertices in the same color. Now, we call this vertex x1 a blue vertex, and we repeat the argument. So we pick a vertex x2 in the blue neighborhood of x1, and we look at the neighbors of x2 in u1. At least one of the colors has at least a half of the vertices. So let's say in this case it's red, and we call this vertex red, and we repeat the thing here. We pick another vertex, and so on. So what we find here is a sequence of vertices. And what's the idea? So if we pick this vertex xi, it's going to have all the edges going to the right are going to be in red. This is the very same idea as before. And the size condition we have now. So before we have infinitely many vertices here. Now we don't have that information, but now we have that the size of the next set is going to be at least a half of the previous set. So we have this inequality here. So if we run this argument for 2t steps, then we can say, OK, so there are two colors. At least t of the vertices are going to have the same color. So let's say in this case is red. So what we find here is t red vertices, which means that all of them send only red edges to the right. And this is a clique of size t in color red. And I put here this sign here because if we pick capital N to be 4 to the t, then we can ensure that we can run this argument at least 2t steps, which shows that, in particular, shows that not only the Ramsey number of the clique exists, but actually that is at most 4 to the t. Good. So this implies Ramsey numbers exist for every graph, but actually we have some upper bound. So the Ramsey number of any graph is going to be at most the Ramsey number of the clique on size of g vertices, which is at most 4 to the power of size of g. So therefore, OK, Ramsey number of g is well defined. But the fundamental question here is, given a graph g, can we compute or can we maybe estimate the Ramsey number of g? So I will try to answer this question now. But let me first warn you that this is a very, very difficult problem. So let me start with the Ramsey numbers of complete graphs, which is possibly, not possibly, it's the most important problem in graph Ramsey theory, possibly Ramsey theory. So the usual convention here is to write R of t for the Ramsey number of the complete graph on t vertices. So what do we know? So the Ramsey number of the clique on 3 vertices is 6. It's a very simple exercise. You can write it in one line. The Ramsey number of the clique on 4 vertices is an exercise, a much harder exercise, but it is an exercise. But for the Ramsey number of the clique on 5 vertices, we still don't know what is the answer. We know that it's at least 43, and it is at most 46. And this upper bound was shown just last year, in November of last year. And they said in the paper that it took the algorithm has to run for 30 years of computation time. So this is a very, very hard problem. So we don't even know what is the Ramsey number of the clique on 5 vertices. So trying to compute the Ramsey number of a graph in general there's no hope to how to compute it. So the only thing we can hope for is try to get some decent bounds. So what are the bounds that we have? So the first bound that I show you is a very famous bound. It's called the Erdős-Sekeres theorem from 1935, which says that the Ramsey number of the clique on t vertices is at most 4 to the t. For the lower bound, there's another very, very famous result of Erdős from 1947, which says that Ramsey number of t is at least 2 to the power of t half. And let me again prove this result because it's a very elegant proof and it's a beautiful proof, and also one can say that it's the birth of the probabilistic method in combinatorics. So we're going to prove this lower bound here. And if we want to prove such a lower bound in general, if we want to prove that Ramsey number of t is at least is more than x, what we have to do is to produce some coloring of the complete graph on x vertices with red and blue, such that there is no blue and no red copy of a clique on t vertices. That's what we want to prove. So we want to produce some coloring with no red or blue clique. So what's the idea? The idea is to produce a coloring randomly. So let's n to be this number, the number of vertices in the clique we want to color. So what we are going to do is to color the edges of the complete graph on n vertices randomly. So the probability that an edge is blue is going to be 1/2. The probability that the edge is red is going to be 1/2, and all choices are independently. And as everything is independent, the probability that a set of size t form a clique monochromatically is going to be 1/2 to the number of possible edges, which is t choose 2. And we have 2 possible colors, red and blue. So this is the probability. And therefore, how many monochromatic cliques we have? The expected number of monochromatic cliques we have is, the number of possible ways to choose the t vertices and choose t, times the probability that this particular set of vertices form a clique, a monochromatic clique. So if we choose n in this way, one can show that this number is less than 1, and therefore there is one coloring, blue-red coloring of the complete graph with no blue clique of size t and no red clique of size t. So this very simple observation gives this amazing lower bound. And let me show you that actually we don't know much more about this. So this is all that we know until 2023. Erdős and Sekeres in 1935 proved that it's at most 4 to the t. Erdős in 47 proved that it's at least 2 to the power of t half. The first substantial improvement was done by David Collon in his PhD thesis. He proved that we can improve this Erdős-Sekeres bound by this factor here, e to the minus log t over log t. And then another PhD student 2 years ago, actually 5 years ago, but it was published 2 years ago, improved this method of Collon, showing that you can improve this log factor with a log square factor. But in 2 years ago, the group of IMPA Cambridge, they gave the first exponential improvement in Ramsey numbers in nearly 90 years. So they proved that actually it's not 4 to the t, but it's like 3.9999. It's at most 4 minus 2 to the minus 7 to the power of t. So this was the first improvement, exponential improvement in this Erdős-Sekeres bound in 90 years. And this is it's not the best we know right now. Some people have been trying to optimize this method. I'm gonna say something more in the next slide. So the first open problem they're gonna show you is by Erdős. So Erdős, every time he likes a problem, he offers some prize if somebody solved this problem. So this was one of the problems. Erdős in 1969 offered a $100 prize if somebody can find a constructive proof that the Ramsey number of a clique on t vertices is exponential in some c. So it's at least c to the t for some c more than 1. And the best thing we know is a result by Lee from 2 years ago. So he proved that the Ramsey number of t is at least polylogarithmic in t. But this is the best thing we know. For the upper bound, there is another prize. So Erdos offer a price of $250 if somebody can find this limit. And the best thing we know is by this group from last year. So they proved that this is at most 3.8. So they improved this result. They build upon this method to prove that this is at most 3.8. OK, so Ramsey numbers of clicks. It's a very hard problem. We don't know anything in nearly 100 years. So what can we say about other kind of graphs? So what we know is the following. Until now, the Ramsey number of a click is exponential. In general, the Ramsey number of a dense graph is exponential. But we have a very general bound, which was proved by Benny Sudakov in 2009, which is that if we have a graph with m edges, then the Ramsey number is going to be at most 2 to the power of some constant times root m, which is tight. So if we put, if g is a click, it has essentially t squared edges, and therefore this is going to be exponential in t. One thing which is very interesting is that we can find a graph which attain any possible admissible function as a Ramsey number. So this is something that we proved with Simon Piga, Nicolas Sangüesa Matamala. Simon was also a student from here, Nicolas also. So Simon is now a postdoc in Hamburg. Nicolas is a professor in Concepcion. So we proved that for any function f, which is admissible in the sense that it's at least n and is at most Ramsey number of the click on n vertices, we can find a sequence of graphs which has Ramsey number essentially this function, is of order of this function. So for any possible function admissible, we can find an example, some graph, well, rather a sequence of graphs, which attain this function as a Ramsey number. OK, so one thing that Erdos was interested was to classify which graphs have linear Ramsey number. For which graphs G, we can the Ramsey number is going to be linear in the number of vertices. For Bure and Erdos in the 70s proposed the following meta conjectures that if the graph G is sparse in some way, then the Ramsey number must be linear. And the first condition of sparseness was that graph of maximum degree bounded by some constant. So this was proved by Schbatal, Rudl, Semeredi, and Troder in '83. So they proved that for any number delta, there is some constant c depending only on this number delta, such that if G is a graph with m vertices, a maximum degree at most delta, so every vertex is at most delta neighbors, then the Ramsey number is going to be linear, at most c times n. So this was the first in this direction. The second result that we know, or the second important class of graphs for which we know that the Ramsey number is linear, are called degenerate graphs. Possibly you have seen something like this in some courses here. So we say a graph is degenerate if it's locally sparse, in the sense that every subgraph of G has a vertex with at most d neighbors. We can also characterize these graphs in another way. We can, in the following way. So we can order the vertices so that every vertex has at most d neighbors to the right. This is called a degeneracy order. In a very important, really important result in this area, Chong-Woo Lee in 2017 proved that this class of graphs also have linear Ramsey number. So for every d fixed, there is some constant only depending on d, such that every graph on n vertices, which is d degenerate, has Ramsey number at most c times n. So beside these two classes of graphs, we have the hypercube. This graph doesn't belong to any of those two classes. So the hypercube is a graph which has vertices, the sequences of 0 and 1 of length n. And two vertices are adjacent if they differ in exactly one coordinate. So here we have an example of the three-dimensional cube. Bure and Erdos, again, in the 70s, conjectured that this graph also have a linear Ramsey number. So the Ramsey number of this graph is at most some constant times to the power of n, which is the number of vertices in this graph. So again, Qn is not constant degenerate, and the maximum degree is also unbounded. So it doesn't belong to any of the two classes I mentioned before. And the best record we have for this particular graph is by last year, Tikhomirov, who proved that the Ramsey number is slightly better than quadratic. So it's at most to the power of 1.97 times n. So this is the best record we have. It's very, very open. OK. So now let me start with the talk. So all of that was preliminary. So let me now start with the real talk. So this talk is about trees, which is something I've been studying since my PhD. So trees are the most basic, most simplest class of graphs, which is a graph which looks like this. It's a connected graph which has no cycle. So here, connected means that for any pair of vertices, we can find a path between them. No cycles, meaning that, OK, we cannot close any. There's a unique path between those 2 points. So trees are connected and are one degenerate. And therefore, by the result I mentioned before, the Ramsey number is linear. However, by a very simple argument, a very simple density argument, one can show that the Ramsey number of a tree is at most 4 times the size of the tree. It's a very simple density argument. Erdos in 76 conjectured that this very basic bound can be improved by a factor of 2. So you can, instead of having a 4 here, you can replace this number essentially by a factor of 2, by a 2. So they conjecture that for every tree T with n vertices, the Ramsey number is at most 2n minus 2 if n is even, and 2n minus 3 is if n is odd. This bound is very general. It's for any possible tree. This is tight. In the sense that there is some tree with n vertices which has exactly that Ramsey number. And the example is the following: is the star. So the star is a tree which has a central vertex which is adjacent to n minus 1 other vertices. And there is a result, a very well-known result, saying that the Ramsey number of this tree, of the star, is exactly 2n minus 2 when n is even, and 2n minus 3 when n is odd. So this shows that the Erdos conjecture is tight for this class of tree. In 2011, Ji Zhao proved that this conjecture is almost true. So if n is very large, it's a very large constant, then the Ramsey number is going to be at most of any tree with n vertices is going to be at most 2n minus 2. So this essentially is proving the even case, but we still don't know what happened with the odd case. So we still don't know how to improve from 2n minus 2 to 2n minus 3. This is still open. And very recently, with Jasmine Katz and Joseph Skokan, which for 3 weeks, and he left like 2 weeks ago, we proved that we can replace the complete graph on this many vertices with a graph with very high minimum degree. So instead of having a graph which has all possible connections, we can remove some neighbors for every vertex, and the graph is going to be still Ramsey for every tree. But we need some condition on the maximum degree. We need to bound how many neighbors is every vertex in the tree. OK, so this Erdos conjecture is very nice in the sense that it's a very general bound. So it works for any possible tree. So for any tree, we have this upper bound. But for some trees, we can do much better. So this is a very old result by Gerenser and Yarfas, which says that for the path. So what's a path? A path is just something like this. It's a sequence of vertices adjacent to each other. It's something like this. This result by Gerenser and Yarfas from 67 says that the Ramsey number of this path with n vertices is essentially 3n over 2. And 3n over 2 is way smaller than 2n, which is the bound that Bohr conjectured in the 70s. So And this is another very nice thing is that we have a very structural extremal example. By this I mean, if we pick a graph with a complete graph with this many vertices, and we set aside a clique of size n-1, and we color all edges here in blue, all crossing edges in red. In this example, we cannot find a path of length n, which is monochromatic. So let's try to find a path in this example. So if we pick the blue graph has only n-1 vertices, so it is impossible to find a graph with n vertices. So here we don't have enough space. If we try to embed the path here in red, no matter how we embed the path, we are going to be using at least n-half vertices here, but we don't have enough vertices. So in any case, it's a problem of space in this example. So in general, for any tree, Bourdieu says, okay, the worst possible scenario is the star. So the Ramsey number is going to be at most the Ramsey number of the star. Bourdieu proved that for the lower bound is going to be always at least the Ramsey number of the path. And so something is happening here. Something about the structure of the tree is saying is controlling in some way the Ramsey number of the tree. So to explain Bourdieu intuition, let me first note the trees are bipartite graphs in the sense that you can color the vertices of the graph with two colors so that every adjacent vertices like this have different colors. So here we have all the edges go from green vertices to orange vertices. So this is Bourdieu's contraction for the Ramsey number of trees. So suppose the trees T has bipartition classes of size T1 and T2, and say T1 is the largest class. So T1 is at least T2. So there are two constructions. The first construction is essentially the construction showing that the star is, the extremal example for the star. And the second construction is the extremal example for the path. So let's look at this example first. So here we have a clique of size T1 minus 1, completely in blue. Another clique disjoint of size T minus 1, completely in blue, and all possible edges crossing in red. In this example, we have a clique of size T1 plus T2 minus 1, which is n minus 1. Everything here in blue is color blue. And here we have a set of size T2 minus 1, and all crossing edges are in red. In this example, we cannot embed the tree in blue because the blue graphs are just too small. So we don't have enough vertices here. We don't have enough vertices here. If we try to embed the tree in red, then no matter how we try to embed the tree, because the tree is bipartite, one of the parts must be here, and the other part must be here. So since the partition classes have size T1 and T2, here we need to embed T1 vertices in one of the classes. But we only have T1 minus 1 vertices. So again, this is a matter of a space that we cannot embed the tree here. In this case, again, the blue graph is too small. It has n minus 1 vertices. And the red graph is the same problem as before. If we try to embed the tree in red, we're going to be using at least T2 vertices here, and we only have T2 minus 1 vertices. So this implies that the Ramsey number of a tree is going to be always at most the maximum between these two constructions plus 1. So it's going to be at least the maximum between this number, which is the number of vertices in this graph, plus 1, and this number, which is the number of vertices in this graph, plus 1. So it's going to be at least maximum between 2T1 minus 1 and T1 plus T2 minus 1. A very natural conjecture was that, OK, maybe this is the Ramsey number of a tree. So Bourdieu in 74, like 51 years ago, conjectured that for every tree with partition classes of size T1 and T2, and having this condition, the Ramsey number is exactly this maximum. However, this conjecture is false. So shortly after, in 79, Grossman, Harari, and Chloe found a counterexample for this conjecture. And the counterexample is this graph here, which is called a double star. So the double star with parameters A and B which we denote by SAB. So here we have a star with A vertices, a central vertex, and A-1 vertices connected. Another star now with B vertices. So this is the central vertex with B-1 vertices, and they are joined by this edge. So Grossman, Harari, and Klaue show that if they have some relationship between T1 and T2, then the Ramsey number is twice T1, which is one more than what this conjecture says. So this conjecture says it should be 2T1 minus 1. And here they have 2T1. So it's one more than this conjecture. So there are even worse news. In 2016, Norin, Sun, and Zhao found another counterexample, which is even worse. So again, the double star, but now of sizes or parameters 2T and T, they show that it has Ramsey number at least 4.2 times T, essentially. And Bour's conjecture says the Ramsey number should be 4 times T, essentially. So there is a factor 1.2 here, which is missing. There is a number, sorry, a 1.2, sorry, 0.2 extra term here, which is missing. So this is terrible. This is essentially saying Bour's conjecture is really, really false. It's not only false by 1, as in the previous example, it's false by a linear number. And for this particular tree, the double star with parameters 2, T, and T, there's a very nice result of a master thesis of some years ago. So this was proved by this was the master thesis of Freddy Flores, which was advised by Myers. So they proved that the Ramsey number of this star is at most 4 times 2.75 times T. So it's still not quite it's not quite high. It's not quite the lower bound. So okay, so Bour's conjecture is a very nice, very natural conjecture, but it's very false. We have this counterexample which shows that okay, it's very far from what it should be. But all known counterexamples have very large maximum degree. So maybe if the tree has low maximum degree, we still could hope to have some hope that Bour's conjecture is true for those class of trees. And this was actually proved by Haxel, Luchak, and Tingley in 2001. So they proved that if the tree has a small maximum degree, then Bour's conjecture is almost true. So they proved that for any error epsilon, there is some constant C such that if T is a tree with n vertices, again, partition classes T1 and T2, but now the maximum degree of the tree is bounded by this constant C times n. Then the Ramsey number of T is going to be what Bour's conjectured. So this is the number that Bour's conjectured plus some error term, epsilon n. So maybe it's true that Bour's conjecture is true for trees with a small maximum degree. So again, all counterexamples have very large maximum degree. We have an approximate version of Bour's conjecture for trees with small maximum degree, almost linear. So maybe there is some hope to remove this extra epsilon n term here. And this is something we proved it's still in writing, but we proved it, let's say, 2 years ago. It's a very long and complicated paper. So we proved this with Richard Montgomery from the University of Warwick, Junjan, also from the University of Warwick, moving now to Oxford. So we proved that Bour's conjecture is true for trees with maximum degree bounded. So we proved that there is some constant C such that any tree with n vertices, partition classes of size T1 and T2, and maximum degree bounded by Cn, for this class of trees, the Bour's conjecture is true. So the Ramsey number of this class of trees is exactly the maximum between these two numbers. Okay. So I would like to say a few words about this proof. So this is the first time I'm presenting a little bit of this proof. It is impossible to present this proof in 10 minutes, I have. But let me present some key steps on the proof. So the idea is the idea of the proof is a very classic idea in Ramsey theory, not only Ramsey theory, but in extremal combinatorics, which is called a stability approach. So what we try to do is to prove something called a stability theorem, which says that either we can find a copy of my 3T in some color, red or blue, or G should look like the extremal example. So this is what this is the general idea. So we start with the click on these many vertices. We pick any tree T that we want to embed. And we let G to be a blue-red complete graph on capital N vertices. So the idea is to prove that either we can embed T monochromatically in G, or G should look like one of the extremal examples. So G should look like something like this, which is one of the extremal examples, or something like this. Not exactly this, but essentially an almost blue click of size almost T1, an almost blue click of size almost T1, and almost everything in between is red, something like this. So the proof of this stability theorem relies on something called the regularity lemma for graphs, which is a very important result in graph theory. But I'm not going to talk of this part. I'm going to talk more about the extremal part. So I want to say a few words about how to embed the tree in the extremal example. So let me assume that T1 is at most 2T2. Why? Because in that case, this maximum is going to be this thing. The stability result says, okay, if we cannot embed the tree, then G should look like this extremal example. So we're going to have a set of size 1 minus mu n. Almost everything here is going to be blue. We have a set of size 1 minus mu T2. We don't have control on the colors here. And we know that almost everything here in between is going to be red. But okay, this is only 1 minus mu, so we have some leftover vertices of size at most 2 mu n. So the first thing we have to do is to somehow reallocate these vertices. So this thing is very close to a click. This thing is very close to a complete graph in red, complete bipartite graph in red. So the first thing we have to do is to reallocate these vertices. And how we pick any vertex here, if it has many blue neighbors here, we move this vertex to this part. Otherwise, it has many red neighbors here, and we move this vertex to this graph. So after reallocating all these vertices, we're going to have some structure like the following. So the graph will look like this. So we're going to have a set A and B. A is an almost click in blue. It has n plus k vertices. B is some set with T2 minus k minus 1 vertices. So here now we have all vertices in this picture. And in between is almost a complete bipartite graph in red. And this number k is any integer. It could be either positive or negative. We don't know. But we know that it's at most, in absolute value, 2 mu n. So what's the information we have? So the blue degree here is going to be almost everything. So the blue degree here is at least 1 minus 2 mu n. The red degree from here to here is almost everything. So it's at least T2 minus, let's say, 3 mu n. And from B to A is going to be at least, it's almost everything. So it's at least 1 minus 2 mu n. So it shouldn't be that difficult to embed the tree in this situation, because we have almost a click. We have almost the right size. So it shouldn't be that difficult. But it's actually quite difficult. It's really, even if we have n vertices here, it's impossible in some cases. So this is an example found by Komlo-Shakosin-Sameredi in 2001, which says the following. So if we take P to be 1 minus mu, there is a tree with n vertices, maximum degree of the order n over log n, which doesn't embed into the random graph with n vertices and edge probability p. So the random graph with n vertices and edge probability p is a graph with n vertices, and every possible edge appears independently and random with probability p. So in particular, with very high probability, one can show that the minimum degree is going to be something like this. So we are going to have very high minimum degree in blue, like this, n vertices, and this tree that is here cannot be embedded in this graph. So even if we have minimum degree like 0.99999n, there is a tree which doesn't embed in that graph. And the reason is that in GMP, with high probability, there is no dominating set of size of logarithmic size. So this tree here that has this set of logarithmic size, which is covering all possible all possible vertices in the graph. So this is the dominating set I'm telling about. Okay. So what do we do? What do we do in this case then? So let me again do another reduction. So suppose my tree I want to embed has linearly many leaves, let's say lambda n, for sub lambda, which is much larger than mu. So the tree which looks like this. So we have a set of leaves which are these orange vertices. They have linear size. And the good news is that if we remove these vertices, these leaves, we can embed the tree greedily. We can go one by one embedding the tree because we have enough minimum degree. So the minimum degree is at least 1 minus 2 mu n. This is larger than the size of the tree, so we can go one by one embedding the vertices. So the only thing we need to do is to, embed t minus the leaves and then try to extend the embedding. So we have at least more than lambda n vertices which are not used. We need to embed lambda n vertices, so we have space. That's good. However, it could be that after we embed t minus the leaves, there is some vertex here which has no neighbors in the set of leftover vertices. So that could happen if we are unlucky. To fix this thing, what we do is to introduce some randomness. So what's the idea? We embed t minus the leaves randomly. So vertex by vertex randomly, every time choosing uniformly random a vertex in the neighborhood of the previous vertex from the unused vertices. So this set, which is the image of t minus the leaves, should looks like a random subset, and therefore also the leftover vertices. The leftover vertices should look like a random subset. So if we want to extend the embedding, suppose X, this set is really a truly random subset, a truly random set. So if we look at the non-neighbors of this set, so what's the expected number of non-neighbors that this vertex B is going to have in X? Well, the probability that a vertex appears here is going to be size of X divided by the total number of vertices times the number of non-neighbors, which is at most 2 mu times X. So essentially, this is saying if we embed the tree randomly, then the number of non-neighbors that we have here for this particular vertex is very small. So we have chances to extend the embedding. If we embed everything randomly, then this guy is going to have many potentially. So randomness improves this greedy embedding. Oops. I see. Okay, good. So that's one thing. Randomness really improved embedding because every vertex here is going to have potentially a good neighborhood here. So the number of non-neighbors is going to be small. However, if we want to use all vertices, which is a case, we also need that every vertex here has many neighbors in the set of parents, and this is where everything collapses. So if we denote P for the set of parents, C for the embedding, the random embedding, then the probability that a vertex here sends few neighbors here is going to be essentially exponential in the number of parents, which is roughly exponential in some number k, a constant. Why? Because the maximum degree being bounded by this linear term implies that the number of parents is at least the number of leaves divided the maximum degree, which is some constant. This is terrible because it means that the number of vertices in X, in the leftover vertices, with low degree into the image of the parents is essentially a linear proportion of the vertices. So this is saying we need more space in the graph. So what's the idea then? Okay, it's not possible to just embed the tree in one of the parts. So what we try to do is to run again try to run this random embedding, but we are gonna force that the set of the parents are gonna lie in some set with large blue degree to the B part. Why? Because we want to send some leaves to the B part. So we try to embed the tree using this strategy. If this is not possible, what we can show is that the red density here can be improved. We can get a density boost in the red graph. And then maybe it is possible to embed the tree in red. And that's somehow the idea. So either we embed the tree in blue using this random embedding, or we get an improvement in the density here, and then we again run the random embedding technique here in the red graph. So in general, in summary, the stability part is regularity lemma proof, and the extremal analysis combine techniques from random embeddings plus density increment argument. That's a very complicated proof, and we are still writing the paper. Okay, but I would like to. I think I'm. The time I would like to stop here. Thanks very much for the. Okay.
Okay, thank you, Matías. Is there any question? ¿Preguntas? Por allá, partamos por.
So, maybe we have been very hard, but you said that there was a. Oh, sorry. So one question is that there was the first exponential improvement in the bounds for the Ramsey numbers in 90 years or something. You said, what's the idea there? Like, what did they do that wasn't doable in 90 years and that they could do now?
So so the first improvement in the Ramsey number of clicks was by Conlon. He used ideas from pseudo-random graphs. In the result, in this exponential improvement by the people of IMP and Cambridge, what they do was to revisit the original argument of Erdos and Chegues. So this argument that I showed you of looking for picking a vertex, it has very many neighbors in one color and so on. So they improved that technique, this very elementary technique. It's a very elementary proof, but it's 50 pages, but it's a very elementary proof. It doesn't use anything fancy. That's the amazing thing. So all the other proofs are very, very technical, very difficult, but this is you don't need to know anything essentially.
Okay, and another small question, like you explain all of this about your theorem, and maybe I didn't understand anything, but what I understood is that you proved some bound, not the equality.
No, we proved the quality.
No, but in the proof that you showed.
Okay. This is like for the quality. So here, in this part, we have this many vertices. This is the stability thing saying that okay, the graph, if we cannot embed the tree, the graph should look like this. So at the end, we have essentially this picture. This picture has exactly the vertices the Burst conjecture says. Exactly the number. Obviously, there's more cases, but many more cases. But this is one of the cases that maybe one can talk about.
Okay, thank you.
Yeah, thank you. I was confused. What does constructive lower bound mean? You mentioned that. What do you mean by constructive?
Means really you have to define a coloring of the complete graph on many vertices. Probabilistic is not allowed, let's say. Not even pseudo-random.
Yeah, but brute force is not allowed either, I guess, right? So
it's not possible, I think.
Huh?
It's not possible for every n. For
them.
So not even for not even for 5 vertices is no.
And no, the randomization techniques gives you nothing?
No, there's a very specific gap. If you want to do something like that, you need to know what's the number of pseudo-random graphs. That's another problem. A very important open problem. So the typical idea is to define a Cayley graph from some pseudo-random set, but the problem is okay if you are if you can compute the chromatic number of that graph, you can get improvements in the lower bounds. But that's a very important open problem in number theory.
For the talk. So I was wondering whether you know about Ramsey numbers of Erdős-Renyi graphs.
It's not known. It's not known. There are some there are bounds. It is known that it is concentrated around the expected value, but it is not known even what is the expected value. So you can prove using concentration inequalities, martingale, that the Ramsey number is very close to the expectation, but we don't know how to compute the expectation.
Thank you.
Okay. There are no more questions, so that's fine.
So only for the people who live, they are able to in their